Hello everyone, this is mathematics lesson for grade 8. This program is organized by Addis Ababa City Administration Education Bureau in collaboration with Addis Media Network. I'm teacher Mamu. I will teach you mathematics. Okay, so today we will learn about Pythagoras theorem, but before I proceed to the present lesson, I will remind you some of the points that we have seen in our previous lesson. Okay, so in our previous lesson, we have seen Euclid's theorem, and we have seen the proof of Euclid's theorem and some of the examples related with Euclid's, right? So, do you remember what Euclid's theorem is saying? Well, Euclid's theorem states that in a right-angled triangle with an altitude to the hypotenuse, the square of the length of each leg is equal to the product of the hypotenuse and the adjacent side into which the altitude divides the hypotenuse, right? Geometrically, if you have this kind of right-angled triangle, say this is a right triangle at some point here, it forms 90 degrees, you can call it triangle ABC, okay? This triangle ABC is a right-angled triangle because it forms 90 degrees at C. Clearly, this is a right-angled triangle. So, in Euclid's theorem, we need to have one more side that is altitude drawn from this 90 degrees to the hypotenuse, forming perpendicular, okay? If we have these kind of things, Euclid tells us the square of one of the leg BC square is equal to the product of the adjacent side into which the altitude divides the hypotenuse. That means call this as D, okay? BD times the hypotenuse AB, okay? This is one of the formula that we derived in altitude theorem, right? The second formula is we have another leg, okay? AC and BC are legs, and the longest side AB is the hypotenuse. Okay, the square of AC is equal to the product of the adjacent side AD times the hypotenuse AB. Okay, these two are the formulas that we derived in Euclid's theorem, right? If you remember, we just tried to pick out two similar triangles from this triangle ABC. One of the similar triangle is triangle ABC is similar to triangle ACD by angle similarity theorem. And that similarity will help us to derive one of the formula. Again, you can consider another situation like triangle ABC and CBD. Okay, the bigger triangle ABC and CBD are similar again by angle similarity theorem. So based on this similarity, we could derive the second formulas, right? So these two are the formula that we already derived, and we have also seen some of the examples that requires the application of Euclid's theorem, right? Just let me remind you by taking a single example. Okay, good. If you have a certain right-angled triangle, say this is a right-angled triangle, assume this is 90 degrees, because to apply Euclid's theorem, you need to have right-angled triangle, okay? If you don't have right-angled triangle, you cannot apply Euclid's theorem. Suppose we have this triangle. Assume there is a certain altitude drawn to the hypotenuse. Say this is the altitude of the triangle. If you want, you can give any letter to represent the vertices, but you can also make it free if you want. Assume this length is 8 centimeter, and this is 4 centimeter. Okay, so to easily represent the lengths, say this is A, B, C, and D. obviously this AD is the altitude of a triangle. Okay, so now based on this information, you may be asked to find the lengths of AB and AC, right? So the first thing that you need to do is you need to remember what Euclid's theorem is saying, or the formula that can be used in Euclid's theorem. Okay, so based on Euclid's theorem, the square of one of the leg, in this case, in this figure, you can take the square of one of the leg AB square. Okay, forget about this one because this formula works for this situation. Now we are taking this triangle, so we need to take the theorem as it is. The square of this leg is equal to one of the adjacent side, that means BD, times the hypotenuse, the longest side BC. Okay, so if you are asked to find this side and this side, you can use this formula to calculate AB. Okay, so in this case, if the question is to calculate AB, use this product. So BD is 8, a centimeter, and BC is the whole this hypotenuse. It's the sum of these two adjacent sides, which is 12 centimeter, right? So this is 12 centimeter. 8 times 12 is 96. Okay, you can check it. It's 96. So 96 centimeter square. Okay, AB square is 96 centimeter square, means AB is the length of AB by taking both sides by radical. You can take these two equations on both sides by radical. So this AB becomes a square root of 96 centimeter square. Okay, 96 is not a perfect square. You can put it in the bracket, I mean in the radical. So centimeter square can be taken out. So this can be written as square root of 96 centimeter. But you can rewrite square root of 96 in a certain different ways. Okay, because 96 can be written as 4 times 24, okay, or in other form, okay. You may have different ways of giving the answer for AB. Okay, it can be 2 root 24 or other forms, right? So this is the length of AB. The other thing, you can also calculate the length of AC by applying Euclid's theorem. So based on Euclid's theorem, the square of this leg, the square of the other leg, say this is AC square, if you are taking this side, the square of this side is equal to the product of the adjacent side and the hypotenuse. So this becomes CD times AB, okay? So your formula is dependent, okay? You shouldn't memorize this thing. Your formula is dependent on the points that you are given for each vertices, right? So the first thing that you need to do is you need to understand what Euclid's theorem is saying, and you need to understand which one is the leg, which one is the hypotenuse. That is a very crucial step of calculating the unknown sides, right? So AC square is equal to CD, which is 4 centimeter, times CB, the hypotenuse, which is the sum of these two segments, so which is 12 centimeter. So 4 times 12 is 48, right? So centimeter times centimeter is centimeter square. So this becomes 48 centimeter square. Okay, so now you can take both sides by radical. So this becomes AC is equal to square root of 48 centimeter square can be taken out from the radical, so it becomes centimeter. This is the answer, but you can also rewrite this square root of 48 in a different ways, because here 48 can be written as 16 times 3. Okay, so the other ways of writing this answer is AC is equals to 4 radical 3 centimeter. You know why? Because 48 is 16 times, okay? This is 16 times 3. And 16 can be taken out from the radical, so it becomes 4 root 3. Okay, this can be the answer, this can be the answer. So here we've seen how we can calculate the unknown legs given a certain right angle triangle with extra information on the segments of the hypotenuse, right? So if you have the two segments that the altitude divides on the hypotenuse, you can easily find the remaining sides of the right angle triangle. Okay, so these were the points of discussion that we had in our previous lesson. Okay, so today we will learn about Pythagoras theorem. We will see how it can be proved. Then we will see examples that requires the concept of Pythagoras theorem, right? So let's see. Pythagoras theorem. So Pythagoras theorem and its converse will be the last theorem that we will have in our discussion on Unit 5. So before we see what Pythagoras is saying, Pythagoras is the name of a person. He is a mathematician. Okay, he is also a musician. He is believed to be a religious person, okay, in his era. So we will try to see what his theorem is saying, and we will see how the formula of a Pythagoras theorem can be derived, right? So let's see what the theorem is saying. In a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the two legs. Okay, so if you have a right angle triangle, Pythagoras theorem states that the square of the hypotenuse is equal to the sum of the square of the other two legs. Okay, that means geometrically, if you have a certain right angle triangle, okay, if you have a certain right angle triangle, say this is 90 degree, so obviously the hypotenuse is the side which is opposite to 90 degree. Okay, if you say this is length A, this is B, and this is C, this theorem is saying that the square of C is equal to the square of A plus the square of B. So the square of the hypotenuse is equals to the sum of the square of the other two legs. Okay, so these two are the legs of the triangle. Okay, so let's see the proof of this theorem. There are around 6 different ways of proving Pythagoras theorem, but we will not see all the different ways of proving. I will stress the 2 different ways of proving a Pythagoras theorem. Okay, then after we will see examples that requires the application of Pythagoras theorem. So let's see the proof. Okay, suppose we have a certain right angle triangle. Okay, suppose we have a certain right angle triangle. Say this is our right angle triangle. Here, assume this is the longest one, and this is 90 degree. Say this is A, B, C. Okay, So in this case, our target is, if this is a right angle triangle, always the hypotenuse is the side which is opposite to 90 degree. So in this sketch, our objective is to prove AB square is equal to AC square plus BC square, okay? So this is our target, okay? We will prove how this equation can be derived. Okay, to prove this thing, I will construct an altitude drawn from the 90 degree to the hypotenuse. Okay, say this altitude cuts AB or the hypotenuse at some point D. So in this sketch, we can extract or we can observe two similar triangles. Okay, so consider triangle ABC, the bigger triangle, which is a right angle triangle. If you see triangle ABC, I need you to compare this triangle ABC with ACD. Clearly, triangle ABC, the bigger triangle, is similar to ACD. This is similar to triangle ACD. Why do you think these two triangles are similar? Well, you need to compare the two triangles. Clearly, these two triangles have common angle A. A is their common angle, so they have one congruent angles. The other thing, triangle ABC forms 90 degree at C. So ABC is a right angle triangle forming 90 degree at C, and ACD is also a right triangle forming 90 degree at D. So they have another congruent angles. Okay, so based on angle-angle similarity, these two triangles are similar. Therefore, these two triangles are similar. Therefore, we can derive a certain proportionality, right? As you all know, if two triangles are similar, we can take or we can assume that the ratio of the corresponding sides of a triangle are congruent, okay? There is a proportionality constant. So by this similarity, we can take that AB, if you are taking this AB, you have to take this AC. So AB over AC is equal to take this BC over CD. Okay, so BC over CD. Okay, these two are congruent. You can also take AC by AD. Okay, all these ratios are congruent. So AC over AD. Okay, we can derive this proportionality by similarity of these two triangles. So from this ratio, you can take the first one and the third one. Okay, from the first and the third, you can take AB over AC is equal to AC over AD. Okay, now you can take a crisscross. AC times AC becomes AC square. This is equal to AD times AB. Okay, so this should be AD times AB. Okay, we have one equation. Okay, this is equation 1. You might know this thing in Euclid's theorem, but we need it to prove the formula in Pythagoras theorem. So we have one equation. This equation is derived by taking the similarity of ABC and ACD. Okay, now let's take another triangle. Let's compare triangle ABC with BCD. Okay, this is similar to triangle CBD. Why do you think these two triangles are similar? Triangle ABC and triangle CBD are similar because these two triangles have two congruent angles. Those two angles are B, angle B is their common angle, okay? The other thing is triangle ABC forms 90 degree at C, and triangle CBD forms 90 degree at D, okay? So these two triangles have two congruent angles. Therefore, these two triangles are similar by angle-angle similarity. Okay, now if these two are similar, you can derive some ratios by definition of similarity. Now let's take the ratio. So when we take the ratio, this becomes AB over CB. This must be the same as BC over BD. And lastly, AC by CD. Okay? Now take the first two. Okay? We don't need the third part. All these three are equal, but you can take these two. Now, by taking these two and crisscrossing, you will get, okay, you will get BC times CB, okay, CB and BC are the same. So BC times BC is BC square. This must be the same as the product of BD times AB. Okay, this must be the same as BD times AB. Now we have another equation. Okay, equation 2. Now let's add directly equation 1 and 2. We will see what will happen. Okay, so when we add these two, we get AC square, okay, AC square plus BC square is equal to, okay, adding these two is the same as adding these two components, right? So this is the same as AD times AB, okay, AD times AB plus BD times AB. Now look at these two terms. In these two terms, we have something in common, which is AB. Okay, AB is common, so you can take it out. Then when you factor out AB, inside you will get AD plus BD. So AD plus BD. Okay, now look at what AD plus BD looks like. What is the sum of this segment AD and BD? The sum of these two segments gives us AB, which is the hypotenuse. In place of AD times BD, I mean AD plus BD, you can substitute AB. So this becomes AB times AB, right? Now, AB times AB is something, the product of something with itself is square, right? So AB times AB is AB square. Look, our objective is to prove that the square of the hypotenuse is equal to the sum of the square of the other two legs. That means AC square plus BC square must give us AB square. Okay, so as you can see here, we are able to derive AC square plus BC square is equal to AB square. Therefore, you can conclude that the sum of the square of the two legs, okay, AC square plus BC square is equal to AB square, which is exactly the same as what Pythagoras theorem is saying. Okay, based on the proof of Pythagoras theorem, let's see some examples that requires the concept of Pythagoras theorem. Okay, so let's see the first example. In the figure below, find the value of x. Okay, Here we have different triangles. Say this is a triangle with 90 degree at some point here at this vertex, and say this is 6, this is x, this is 10. Okay, this is the first question. The other one is assume we have a triangle with side lengths 4 centimeter, 3 centimeter, and x. And the third one is say this is 13, this is 12, and this is x. So suppose we have these three triangles. In each of these three triangles, we have a certain unknown sides. So we will see how we can find these unknown sides, right? Since all these are right angle triangle, we can apply Pythagoras theorem. Okay, whenever you apply Pythagoras theorem for the first triangle, the square of the lengths of each side, the sum of the square of the lengths of each side must be the square of the hypotenuse. So here we can do it like this. So the square of 6 square, plus x square must give us 10 square. Okay, so 6 square is 36. 36 plus x square is equal to 100, right? Now you can take 36 to the right side, then this equation becomes x square is equals to 100 minus 36. Okay, the difference between these two numbers is 64. So x square is equal to 64. Okay, so you can take both sides by radical, and this equation becomes x is equals to square root of 64. Okay, as you all know, 64 is a perfect square, which is the same as 8 square, so it can be taken out from the radical. So this becomes x is equals to 8. Okay, so the unknown side in the first right triangle is 8. Now let's see the unknown side in the second triangle. Okay, as we did in the first case, we will apply Pythagoras theorem because it's a right angle triangle. Don't forget, we can apply Pythagoras theorem and its formula for only right angle triangle. So as you can see in this figure, the side which is opposite to 90 degree is x. So this side is the hypotenuse. So the square of this length, or the square of the longest side, is equal to the square of the other leg plus the square of the second leg. Okay, so 3 centimeter square means 3 centimeter times 3 centimeter, which is 9 centimeter square. Okay, this is 9 centimeter square plus 4 square means 4 times 4, so it becomes 16 centimeter square. Okay, 4 centimeter by 4 centimeter is 16 centimeter. So the sum of these two numbers is 25 centimeter square, right? So this is 25 centimeter square. So x square is equal to 25 centimeter square means you can take both sides by radical so that you will get the value of x. So x becomes 5 centimeter, okay? Taking both sides by radical will give us 5 centimeter. So the length of the unknown side in the second triangle is 5 centimeter, right? Similarly, we can obtain the unknown side of the third triangle. Okay, in the third triangle, clearly 13 is the hypotenuse. So you can say 13 square is equal to 12 square plus x square. Okay, 13 square means 13 times 13, which is 169. Okay, you can check it. 169 is equal to 12 square means 12 times 12, which is 144. Okay, 144 plus x square. Okay, now you can take 144 to the left side. So this becomes 169 minus 144 is equal to x squared. Okay, so this difference is 25. The difference between these two numbers is 25. It's a simple calculation. You can do it orally. So then this is 25 is equals to x squared. So now the last step will be taking both sides by radical. So this becomes x is equal to 5. Okay, so you can take both sides by radical. The value of x becomes 5 unit. Okay, so this is how you can apply Pythagoras theorem to find the unknown side. But there should be two sides. Okay, in each of this situation, you need to have two sides of a triangle so that you will be able to calculate the third unknown side. Okay, this is how we can apply Pythagoras theorem. There is also a converse of Pythagoras theorem. Already we have seen that Pythagoras theorem says the square of the length of the hypotenuse is equals to the sum of the square of the two legs. Okay, and we have seen how it can be proved. And the converse of the Pythagoras theorem tells us if we have a right angle, if we have three sides, the longest one and the other two legs, then the converse of this theorem states that if the square of the longest side is the sum of the square of the other two legs, then the triangle is a right angle triangle. Okay, so that theorem helps us to identify whether the given triangle is a right angle or not. Okay, so I will not write what the converse of Pythagoras theorem is saying, but I will use a single example to explain what the converse of a Pythagoras theorem is saying. Okay, so look at this example. Determine whether the triangle with sides 20 centimeter, 15 centimeter, and 25 centimeter is a right angle triangle or not. A right angle triangle or not. Okay, in our previous example, we were calculating a certain unknown sides by giving two sides, right? And we applied Pythagoras theorem to find the third unknown side. But in the converse, as I've said earlier, the converse of the Pythagoras theorem states that if the square of the longest side is equal to the sum of the square of the other two legs, then that triangle is a right angle triangle. So based on this converse, let's see whether this triangle is a right angle triangle or not. Okay, so you will do like this. Okay, so look at all the sides. Clearly the longest side in this triangle is 25. Okay, clearly 25 is the longest side. So the only thing that you can do is you compare the square of 25, whether this is equal to 20 centimeter square plus 15 centimeter square or not. If this sum is the same as this one, okay, if this sum is exactly this one, clearly the triangle is a right angle triangle. If this sum is different from the square of this number, then the triangle is not right angle triangle. Okay, this theorem, the converse, helps us to identify whether the triangle is right angle or not. So now, as you can see, 25 centimeter square means multiply 25 by 25. Okay, check it. 25 by 25 is around 625. Okay, The square of this number is 625, and the square of 20 is 400. Okay, 400 centimeter square, and the square of 15 is 225, right? So it's 225 centimeter square. Now you can see that the sum of these two is exactly 625 centimeter square. Therefore, our conclusion will be, therefore, the given triangle is the given triangle is right angle, right? So this way we can check whether the triangle is right angle or not. Okay, so today we have seen what Euclid's theorem is saying, and we have seen how it can be proved. We have also seen some examples that requires the applications of Pythagoras theorem. So this is all for today. I hope you enjoyed the lesson. Thank you for watching.